Okay, guys, we just talked in the previous videos about passive transport and active transport. I touched upon simple diffusion. That's really, as its namesake, simple. You go through the membrane, or you go from high. You go from high to low concentration. If you're small and nonpolar, you can go through membranes, phospholipid bilayers. And even if there is no membrane, you're still gonna go from high to low. In your teacup, think about the T from the T-bag. You just go out and spread. The facilitated diffusion, in case you're non-small or polar or both, so you kind of big and polar or both, and that requires some facilitation, so some tunnels through the membranes to go through. So that's in the case you have a membrane or some obstacle to block the diffusion, and it's still passive because as opposed to active, it does not require energy, whereas active requires energy. And in that case, you are big or polar or both, and you want to go across the membrane, you will require across the membrane against your concentration gradient, you will require energy. So if you want to go from low to high, you will require energy. To do that. There's a form of passive transport I want to touch upon right now, and it's osmosis. And the thing about osmosis is it seems like it's gonna be different because you look at the example and you're just like, oh my god, that's a different thing. Yeah, no, it's not different. It's exactly the same thing, but it's about the movement of the solvent rather than the movement of the solute. So remember the difference: the solvent and solute. How do you differentiate those two? The solute is dissolved in the solvent. That's it. So at the end of the day, you can have several solutes, but there's only one solvent, and the solvent is always the molecule that's the most abundant in the solution. So it doesn't mean it's always water. It can be alcohol. It can whatever the solution has in most abundance will be the solvent, and it needs to also dissolve the other solute. So imagine you have no solvent and only solute, it's not a solution anymore. So you can have a bunch of salt, a bunch of dirt, a bunch of gravels, a bunch of sand. There are only solutes in there. There are no solvents, right? There is no solution. A solution needs to be liquid. In that case, it could be water dissolving the solutes, being the salt. And we talked about in previous lectures how the salt molecule can be broken down. Those ionic bonds between Na plus and Cl minus. How the molecule of waters with the remaining charges on the oxygen and hydrogen atoms, those remaining charges can encapsulate the Na plus or Cl minus. We talked about it, go back and revise that. But it can also be ethanol. Ethanol is a really good solvent. It can also be like Coca-Cola if you use it to take off the rust of your car. And yes, it does work, and it's pretty bad. It's pretty bad. It means it's super acidic, so when you drink it, you drink that. Okay. Now that you know the difference between solvent and solute, osmosis. So if you think about diffusion, usually the movement of solute in the solvent. We talked about it. We usually talk about movement of solute from high to low concentration. Now, in the case of osmosis, there is something that prevents the solute to move. So now you have to imagine a phospholipid bilayer, and we're going to take that example. I know it's a slightly different example in the book, but in the PowerPoint, but I want to talk about that this way. The phospholipid bilayer is called a semi-permeable membrane. And why is it called like that? Well, semi means half, like over time. Permeable means letting through something. And membrane. So that's a membrane that lets some things go through, but not all. And that's exactly what a phospholipid bilayer is. If you remember, a phospholipid bilayer lets the small non-polar molecule through, but not all of them. Not the others. Not the ones that are polar and or big. So, if we now look at a molecule of whatever, it doesn't really matter, we're going to take X. X is a solute, and is highly concentrated outside compared to inside. And that's just arbitrary decision here. We have the in and the out, so that's the out, that's the in. So you would think that X will go through this way, right? But This is a semi-permeable membrane, and X is too big. The molecules of X are like giant polar molecules, and they won't be allowed to go through. And so we have a problem, because that's how it would go, right? There is a potential energy to carry X from high to low concentration, but that doesn't work due to the size. And so what's going to happen is, just simply due to that differential, the molecules of the solvent, and in this case we will take ethanol, just to shake things up and make sure we understand it's not always as it's always water. And ethanol, and I'm just going to, ETOH is the way we abbreviate ethanol. Ethanol is similarly concentrated outside and inside. There is no difference in concentration of the solvent. And yes, it makes perfect sense, because the solvent, by definition, dissolves everything else in itself, and it's small enough to go across. So the solvent can go either way, right? Since that solvent can go either way, and there is a high movement needed of those by the principle of entropy, there's a lot of movement needed from those X molecules towards the inside of the cell. The plan, the end of the day, entropy is to get those two to be equal. So you need to increase here, and you need to decrease that. And so how would you decrease the concentration of X outside and the concentration of X inside, increase inside? Well, think about what the concentration of X is. The concentration of X is, and I'm going to write it there, the concentration of X is equal to the number of X molecule either side divided by the solvent, the number of ETOH. This is literally how you get the concentration, is how much X you have compared to how much solvent you have. So to change the concentration, if you are able to go across the membrane, which in this case you are not, but if you were, you would change the big X here, because you would literally take molecule from the outside to the inside. But that's not possible. We cannot influence that this way, because X is too big and charged to actually go across the membrane, and there is no facilitated diffusion here. There is no protein allowing X to move across. So you want to think of X as an inorganic thing. The cell doesn't really use it, doesn't really need it, so you can think of it as the salt, for example, if you want. And so now, the only thing you can influence is the concentration of the solvent. It's the amount of molecules of solvent. And this is what's going to happen, because the principle of entropy is respected, and the water concentration is going to change, or the ethanol, in this case, the solvent, is going to change, because it can fully move. So remember, we want to decrease X outside. Okay, to decrease X outside, we are going to need to increase the concentration of the solvent. That's the only way to get that smaller, because we cannot change the denominator, the numerator, we're going to have to change the denominator. So we're going to have to increase ETOH outside, which means that ETOH is going to go out that way. Because it can move freely, it's going to go out that way, and that's going to increase that, and by definition, decrease this, right? So X is going to decrease outside. Now we want to increase X inside. So to get that bigger, you either get the numerator bigger, or you get the denominator smaller, right? So you need to take some of the ethanol inside and to send it outside. Oh wait, that's exactly what we needed for that one to happen. So by definition, by decreasing the concentration of X outside, we increase the concentration of the X inside simply by adding the solvent moving against the concentration of X's, right? You cannot move X with this concentration along this concentration gradient. So you're going to move the solvent against the concentration gradient, right? And that's really all there is. That's really all there is in the osmosis. And you can think of it as this, moving across the concentration, solvent moving across the concentration of solute, because the solute is incapable of moving across the semi-permeable membrane. Another trick is to think of osmosis simply as passive diffusion of the solvent this way. Because think about it, the concentration of X is number of amount of X over ethanol, right? But the concentration of a solvent is the number of solvent, so in this case ETOH, over the number of solute, in this case X. So you have a concentration of ethanol, if you consider that as the solvent, that is smaller outside because there is more X than inside, right? And so now you can think of osmosis as the solvent going down its concentration gradient. It's another way to think about it. If that just confused you, go back to just thinking of solvent going against the concentration gradient of solute when solute cannot cross the membrane. I know other people can think differently, and I certainly love thinking about the solvent going down its concentration gradient as well, simply due to the fact that the solute cannot move across its down its concentration gradient. The solvent is going to move down its concentration gradient because it can. So those are two different ways to think about the same thing. Pick the one that works for your brain and roll with it. Okay. I'll see you next time. Take care.